Hello, in this session I'll do a quick overview as to what equilibrium is and to calculate the equilibrium constant Kc, but I'll go through some harder questions in another session. So the common mistake with this is that someone will look at this and think this means equilibrium. This means reversible. It can mean that a reaction is at equilibrium, and so we will address what dynamic equilibrium is and then also to calculate Kc. So this means reversible, and one such example that is reversible but not at equilibrium would be this one. If we have hydrated copper sulfate, which is blue, if we heat it up, the water will evaporate, making white anhydrous copper sulfate. When we add water again, it makes it blue again. So this is reversible, but not necessarily at equilibrium. And this reaction would not happen maybe straight away, but you need to do that yourself and add water. And so we say it's reversible because we can get it back fairly quickly. Unlike if you were to burn wood, you make carbon dioxide and water. Arguably, photosynthesis can make the tree or plant again, but that is too many steps and too long. So reversible needs to be something that can be quite easily undone in chemistry. And whilst we're here, what does this dot mean? This dot means that we have 5 waters in ionic structure of copper sulfate, but we write it this way because if I were to write it like this, then it would be a bit confusing. So this dot may appear in other formulae, but it just tells you that you've got 1 to 5 in this particular example. So this should be read as one whole compound of hydrated copper sulfate. So another characteristic of a reaction at equilibrium is to be done in a closed system. And so to give you some examples of an open, closed and isolated and what they mean, we have a cup of coffee here, a thermos flask and a bottle of water. So the cup of coffee is said to be an open system where heat can be transferred because it can get colder if I were to leave it out. And if I were to knock it over, the matter can escape and it's also evaporating. Whereas a closed system is one where heat can be transferred, but the matter is not, that is staying inside the bottle. And then the thermos flask is to, say, an isolated system where we have a vacuum maybe around it to reduce the amount of energy transfer so it stays hotter or colder for the longest time period. So the reaction at equilibrium would need to be done in a closed system. And the reaction of A, B, C, D should be read as making C and D, but it should also be read as the reverse reaction happening at the same time if we were at equilibrium. And so another important thing to appreciate is a reaction may not be at equilibrium yet, and so we need to wait time in order to achieve that. And so both the forward and backward reaction are simultaneously occurring at the same rate would mean that we've achieved equilibrium, but the concentrations of C and D may not be present yet, so we need to make it. It could be there at time 0, but we might just have A and B, at which point we have high amounts of A and B and they will start reacting, and they will start off reacting faster because we have lots of them, and then it will decrease over time because we have less A and B particles, and then when we make C and D they'll get in the way of them colliding. But because C and D can turn back into A and B, the rate in which that reverse reaction occurs will start to increase. So the rate in C and D will start to increase over time as more C and D is made. And then we get a point eventually where the rate of the forward and reverse reaction is the same, and that is when we have achieved equilibrium. And there might be tiny fluctuations in terms of the rate, one speeds up, one slow down, but if you were to zoom out, so to speak, then it would look like a flat line. So this point would indicate that we have achieved equilibrium. So we have to wait a little while to do that, but depending on the reaction and the conditions, it has to be closed, for example, it has to be favourable, then we can get to that point. So this is my favourite animation that shows equilibrium. These little ants, see them go. We have 2 different rock piles in different amounts, so the rate of those ants moving are the same, but the rock pile distribution is not the same. So I might have 75% reactants to, say, 25% products, and we would say that the reaction lies to the left, the position of equilibrium lies to the left. So we are at equilibrium where the rate of the forward and reverse is the same, but they may not necessarily be 50-50. And if I were to do a change, and at GCSE you may also recall saying, for example, the position moves right. So even if it does move right, it could still mean that I have majority being reactants. I could have 60% and versus 40%, but we just say it moves right to change the amounts in terms of the position. But one of these ants would have to temporarily speed up or one slow down when equilibrium is destabilised, and then we'll need to re-achieve that. And I'll explain that later on in relation to the reactant quotient. But that's what we mean by dynamic equilibrium. Those ants are moving at the same rate. They are negating the effect of each other. The piles appear constant, and we are now at equilibrium. So characteristics, just to recap, we have a reaction in a closed system. The forward and backward reactions are occurring at the same time, at the same rate, and the concentrations of reactants and products appear to remain constant. If we were to write an equation, this is the point where you need to introduce Kc. So using the example here, we have a system in which all are in the same phase. If we were to investigate the formation of hydrogen iodide over time, so 2HI, and allow an equilibrium to be established, then we can say how much product is made in relation to reactants and introduce an equilibrium constant, in this case Kc. So the square brackets means concentration in moles per unit volume. Even though these are gases, we're going to use square brackets. Another equilibrium constant Kp looks into the pressure at equilibrium, but in this case we're just looking at the amounts. Kc is only affected by temperature, and then we also raise to the power from the stoichiometric ratio of the equation. So I have 2 hydrogen iodides here, so that's why I've got 2 there, and only as a ratio 1 and 1, and therefore my reactants are 1 and 1. If my equilibrium constant value is greater than 1, then this means I have more products in relation to reactants. So for example, if I had 75% products and 25% reactants, then my equilibrium constant would be 3. And this tells me I've got more products in relation to reactants. If I had an equilibrium constant that is pretty much 1, or 1, then that means I have 50-50 of both reactants and products, because say 50 products over 50 reactants is an equilibrium constant of 1. And if I had a equilibrium constant that is less than 1, then that means that the mixture will contain mostly reactants and the position will be lying to the left. Using some hypothetical numbers to show how the equilibrium constant will remain constant, I've got an expression here. So the amount of C and D as products being made in comparison to my reactants A and B, I've got a Kc expression there. If I were to decrease the value of C, then my value for the equilibrium constant will no longer be the same, and actually now it becomes what we call the reactant quotient or reaction quotient. And my ants wouldn't be moving at the same rate anymore, so one would have temporarily slowed down or sped up in relation to this, so to speak. And so my equilibrium has been destabilised, and so we refer to that temporary destabilisation as being the reaction quotient. So if I were to put some numbers in, so if Kc was 2, this can be achieved by having 2 times 1 over 1 times 1. If I were to decrease the amount of C, in which case is this one, and I made it 1, then that changes my equilibrium constant and destabilises it, and so this is now referred to as the reactant quotient, or in this case Qc, and so this comes out as 1, so it's no longer being constant. So in order to make it go back to being constant again, then the numerator would need to increase, and this is where, if you remember from GCSE, if you decrease the amount of C, then you need to increase the amount of C. It does this by moving the position to the right, so I get more C again. So one way to do that would be to decrease my reactants, so this value becomes 0.4. That would also then increase my numerator a little bit, so let's say it's 1.2, and that's increased that to 3, but I've overshot it, and so it will keep trying to do that until it achieves a value of 2, so a bit of backwards to and fro. But in order to get my equilibrium constant being the same again, then my products would need to increase. I mean, this would increase too, but just to make the numbers work. I hope that illustration kind of helps you understand. So in order to keep the equilibrium constant, my numerator and denominator values would need to change in order to make that possible. But in that temporary amount of time at the beginning, the equilibrium constant is referred to as the reaction quotient, and then once equilibrium is re-established again, then we get that value back again. So only temperature will alter the value for the equilibrium constant. Let's say there will be fluctuations in producing reactant and quotient, but the Kc value will be re-established. and again, yeah, so only temperature affects Kc. So here's an easy question, which if you had the equilibrium concentrations provided to you, then you just substitute them into the expression. So just to quickly go through this, in another video I'll explain about how to go through and calculate the equilibrium moles, and pretty much the same as this after that point. But to work this out, so the reaction is where I was speaking about earlier, so hydrogen iodine makes hydrogen iodide, and the equilibrium concentrations are 0.14, 0.04 and 0.32. And so remember that the key word here, equilibrium concentrations, is telling me that it is at equilibrium already, so therefore I do not need to work out in the initial moles, if you understand that type of question. But just to finish this off, all we need to do is just substitute those values into the expression. So 0.32 squared over 0.14 times 0.04 gives me a Kc value of 18.3. My units cancel out because I've got 2 on top and 2 on bottom. So we say that the units is no units. And this means that my position of equilibrium lies heavily to the right, which means majority would be product in comparison to reactants, as my equilibrium constant value is greater than 1. And I hope that helped. So in another video I'll explain about going to do mole calculations with initial moles, but otherwise if you want more support, check out the other videos, and have a good day. Bye bye.